Hello, my name is Stephen Mumford, and my colleagues are Adela Chen, Austin Stover, CJ Wilson, and Louise Yang. And our semester project is using context encoding networks to improve the algorithm of cone beam computed tomography. The significance of this research is to eliminate the trade-off between cone beam CT, which is cheaper, but requires more radiation exposure than fan beam CT. CBCT also produces less than standard images, and by addressing these issues in our research, we allow more people to have access to CT imaging, and with increased affordability, this will allow for more imaging to be used in different diagnoses. Therefore, our specific aims are to create a basic model, including this context encoding module, to reduce the required radiation exposure. Then we will train a convolutional neural network with the context encoder to process these CT images, and then we will test the algorithm with known objects and phantoms.
A paper in 2016 performed a comparison of image quality and dose between cone beam CT and band beam CT. Cone beam CT systems were shown to give grainier and less uniform images than band beam due to being intrinsically more prone to scattering, beam hardening, and artifacts. Cone beam CT was also shown to give greater secondary cancer risk and irreparable damage to critical organs due to providing 2 to 3 times more radiation per scan than band beam CT. A paper in 2017 demonstrated how deep learning can be used to lower radiation exposure by improving CT image reconstruction. A symmetrical convolutional and deconvolutional neural network named Redkin was used to improve noise suppression, structural preservation, and lesion detection in low-dose CT. Previous methods to improve the reconstructed image of low-dose CT were sonogram, domain filtration, iterative reconstruction, and image processing. These previous methods all had their own set of issues, such as spatial resolution loss and sonogram filtering methods, when the edges in the sonogram domain were not well preserved. Our approach will apply the concept of using deep learning with an added layer of context encoding to improve image quality.
A paper released in 2019 used the context encoder network CENet to improve 2D medical imaging segmentation in several different tasks, such as optic disc segmentation, retinal vessel detection, and lung segmentation. This method was able to capture greater high-level information and better preserve spatial information due to its 3 major components: a feature encoder module, a context extractor, and a feature decoder module. This context encoder method outperformed various other state-of-the-art medical segmentation methods. However, it only validated using 2D images. We propose to apply this method to cone beam CT, which is inherently 3D. In addition, the approach of context encoding in CNN is general, and we can therefore apply it to a broad range of medical segmentation tasks beyond what was tested in the CENet context encoder network for 2D medical imaging segmentation. We also plan to implement a generative adversarial network, GAN, that we will go into depth later in a slide. We are trying to use context coding to generate an adversarial network effectively guarantees the quality of CT reconstruction images in the case of incomplete projection data and achieves the purpose of obtaining CT images that meet the clinical diagnosis requirements with reduced X-ray dose.
For the approach, this flowchart shows the general procedure of this project. It mainly contains 3 big parts: data pre-processing, training our context encoding-based neural network, and testing. I'll go over the 3 parts one by one. In the data pre-processing stage, we're transferring 3D data to 2D data because the algorithm we're using is not able to process 3D data. And the data set we need for training is the incomplete data scanned with CBCT through limited angles and a traditional complete CBCT scanned data of the same object. Then we're slicing the 3D data along the x-axis to get a bunch of 2D data. After the data being prepared, we can start some training. Since this part contains some new concept, I'll introduce the neural network we're using in this project a little bit. So we're using the generative adversary network structure here. It contains 2 models, the discriminator model and the generating model. It is called adversarial because the 2 models are actually contesting with each other. The target of the discrimination model is to successfully tell what data is generated and what data is real. However, the target of generating model is to generate data that cannot be distinguished by the discriminator. Through this kind of contest, the 2 models will improve and eventually get to a settling point. So the training part including 2 stages. During the stage 1, The real sample data is input into the discriminator. Since all the samples are real, we expect the output of stage, which is dx, to be as close to 1, which represents true, as better. During the stage 2, we first input some noise. This will represent the missing places of the data we just prepared, and let the generator to generate samples to fill in the missing places. Then the output of the generation model is input into the discriminator. Again, at this point, since all the data are fake, we want the output of the discriminator to be as close to 0 as better. This is the general idea of how generative adversarial network works. Here's the math behind that. Dr. Ian Goodfellow solved this optimal solution of this equation to be d of g of z equals 0.5. The 0.5 is like 50-50 chance. It means the result of the last two models contest is that the generator can output fake data, which is difficult for discriminator to determine whether the data is fake or real. Now we can use context coding network to generate a usable adversarial network structure for our limited angle co-beam CT. We are mainly divide the network into two parts. The generation network uses a convolutional neural network layers to build a network structure similar to an autoencoder, which analyzes the image feature expressions of the incomplete 2D data through the convolution process, and then the decoder predicts the missing structure of the two-dimensional data. First, the real objection data of the missing part will be input into the discriminator. The network will update the weight of the discriminator network according to the output probability value between 0 to 1. This is to improve the precision of the discriminator network. In the second stage, the prediction data output by the decoder is input into the discriminator network. The network will update the weight of the discrimination network according to the probability value of the output. Therefore, the generating network and discriminating network plays a zero-sum game. After continuous weight updating, the generated data of the generating network GZ is closer to the real data. The final goal is that the discriminator cannot distinguish whether the generated data is real or fake, similar to what we said last time. Due to the limited time, the math and the algorithm behind the context encoding and the neural network will not be explained here. Let's come back to the big picture. After the data is prepared, the generator will be trained using the generative adversarial network. After the discriminator can no longer tell whether the input is real or fake, we can then test the system with another set of incomplete data scanned with limited angle co-beam CT.
So there are several potential issues that might emerge with our neural network strategy. We might have just generating and discriminating models that overfit the data sets that we're training them on. That is, they won't in the real world actually do well because we don't have enough images in our data set. So to increase the number of images in our data set, we can use progressive resizing and linear image transform techniques. That is like rotating and stretching the images. And we can also balance the number of images for our training data with the number of images for our testing data. Secondly, the optimal solution for our neural network might not decrease error enough. It might not produce adequate accuracy. And to improve this, we can make sure that our convolutional neural network hyperparameters are correct, and we can also change gradient descent methodology, say between momentum-based and atom optimizer gradient descent. And finally, we can put multiple neural networks together to create an ensemble. Finally, and the most important method for managing risk here is to create multiple dosages of training and testing data so that our CBCT images aren't too blurry for our convolutional neural network to discern features of illness and let us do diagnoses. If we have multiple levels of CBCT data, we can accurately determine how much our convolutional neural network works. And even if it isn't a fantastic neural network, we can still do some diagnosis and some improvements of our CBCT images.